Okay, number 6, so CV6. Right, so we have 4 curves. This is, by the way, note this is a lot like that example from the section. Right? So let's draw the curves. I have x squared y equals 1, x squared y equals 2. Okay, so those curves are going to look kind of like, let's see here now. So x squared,
I mean, treat them as rational functions.
I'm sorry?
Like the first
Yeah, that's right. They're kind of like little hyperbolas,
yeah.
kind of. And I just have to make sure to get my act straight here. Looking at x squared y equals 2, when y is 1, x is only the square root of 2. But when x is 1, y is 2. So yeah, these curves look kind of like this. They're sort of they're closer to this axis than they are to this axis. Just a little bit. And then these other curves look kind of like this. I'm exaggerating. They don't look that bad, but they cross over. That's the point. Okay. So these region that we're interested in is this. Given the equations there, I'm going to define an h function. It goes the other way, of course. That gives u and v as functions of x and y, like so. I'm going to use x squared y and xy squared.
Is there a certain order that you put them in?
No, it doesn't. It doesn't. If you flip them, it doesn't really make any significant difference. You're going to get a minus sign somewhere that you'll have to take an absolute value, and the integrand will be a little different. But in terms of the final answer you get, it doesn't make any difference.
And we knew those were the outputs. Is it because those are level sets? That's what you need.
Yeah, that's right. You choose these functions because these are the functions whose level sets you're looking at, and that's why I get to assert over here that in the UV plane, like these first two curves, those first two curves are where this is equal to 1 and 2. Therefore, it's where u is equal to 1 and 2. And so I just get to say 1 there and 2 there, and I'm going to have little, curves like that, straight lines. Yeah, these first two curves that I drew.
Okay.
Yep. That's where I set x squared y equal to 1. This is x squared y equals 2. That means that u is equal to 1 and u is equal to 2, and those are straight lines over here in the UV plane.
Okay.
And then likewise, these are where v is equal to 3 and 4. That's really not to scale. I kind of blew the art on that. Sorry about that. Doesn't matter. The point is it's a rectangle. Okay. So we are interested in computing the area in the xy plane. Oops, sorry, dx dy. That's how you compute area in the xy plane, integral of 1. So I'm going to argue, and I'm going to use that cool sort of Jacobian notation with that looks like a fraction. I'm going to argue that that's equal to a double integral of partial xy, partial uv, du dv. And what I like about this is that a double integral du dv, that's just an integral over a rectangle, and we love rectangles. Right? Okay. All right, so got to compute those partials. So partial xy, partial uv. Well, I don't know x and y as functions of u and v. I have that the opposite way. So what I can compute most directly is partial uv, partial xy. That is just the determinant of, and now I just got to compute the Jacobian of this function. So the partials with respect to x are 2xy and y squared. The partials with respect to y are x squared and 2xy. And altogether this determinant is, well, let's see, we have 4x squared y squared minus 1x squared y squared. That's 3x squared y squared. So therefore, shame on me. Shame on me. I forgot my absolute values. Embarrassing. That's not good. Okay, so all this, we need to take absolute values. But conveniently, that's just 3x squared y squared because that is clearly positive.
Because we're in the first quadrant, right?
No, because x squared and y squared are always positive. Yeah. But that's also true. Yeah, that's right, that these intersect in the first. In fact, did it say? Yeah, area in the region in the first quadrant. So x and y are positive, but it don't even need that. Yeah. Okay, so that is partial uv partial xy. What I need is partial xy partial uv. That's the reciprocal, right? So I claim that this guy is 1 over the absolute value partial uv partial xy, which is what we just computed. So I'm going to have 1 over 3x squared y squared du dv. Now we have this problem. Whenever your function goes backwards, you're going to face this annoyance. Oh, sorry, I didn't have that on there. You're going to face this annoyance that because this function's going sort of backwards, everything's going to be written in terms of the independent variable for that function, which is x and y, and I don't want everything written in terms of x and y. I want to rewrite everything in terms of u's and v's. So now I've got to figure out how do I rewrite this in terms of u and v. And that's not, u and v. So that's not so bad if you just look at the formulas for u and v. Note, for example, notice that u times v is x cubed y cubed. So a little side work here. uv is x cubed y cubed. Therefore, uv to the power of 2/3 is x squared y squared, which is kind of what I got here. So I can rewrite this as 1 over 3 u to the 2/3 v to the 2/3 du dv. And so this is your double integral to do over that rectangle. Yeah, that's right. These are your bounds for that's the domain in the UV plane, and you're just going to do that integral. Yep. Everybody good? Okay. Good deal.